as you may have observed, that slowly, after defining the laws of conservation of mass, mentioning their we will be denoting them, we are moving in the direction of developing Bernoulli's equation. And we have mentioned this name a number of times, and this is because this equation is very much used in various flow field situations, that is used by in everyday life by engineers or scientists, mathematicians, and so on, wherever it needs occurs. But this equation basically is derived, and it depicts the laws of conservation of motion, in which mass, momentum, energy, etc. Occurs and reflects. So this is an approximate relation between pressure, velocity, elevation, and is valid in regions of steady, incompressible flow where net frictional forces are negligible. Now you can see how many conditions in this one statement had been introduced. So to be able to derive this equation and to be able to make use of this equation, we must be careful about these assumptions. See the term, it's an approximate relation. So it's not absolutely exact, but it is a good enough relation. That is why this equation is used. And it has been seen in most of the practical situation and experiments that the results are fine. The equation do represent the real fluid flows. So that's why it's valid. But within the limitation of its assumptions. It composes of the parameters, the physical properties that involve pressure, the velocity, the elevation, or what you may call as height, and is valid in the region of steady motion. So we are not talking of unsteady motion. So d by dt probably in most cases will be 0, and also it is mostly used in incompressible cases. By incompressible cases means that d rho by dt is 0. That is the density. Rho is the density, mass over volume, is constant. And also the frictional forces are negligible, are very small, small enough to be ignored compared to the major terms. And therefore, essentially it is saying that it is inviscid fluid. So something like water, for example. And you will see, you will come across the irrigation engineer, the hydraulic engineers, or people who are working with irrigation, canals, and so on. They use it a lot. Despite its simplicity, although the equation in the end is very simple, it has proven to be extremely a powerful tool in fluid mechanics. If it wasn't, we would not be talking so much about it. The Bernoulli approximation is typically used in flow fields outside of the boundary layers. Boundary layer occur where there is viscosity. So it has to be outside the boundary layers. So no viscosity there. And here a picture shows some of the regions where the Bernoulli equation is valid. You can see it is showing that Bernoulli equation is not valid in this region. Sorry, encircling is not very exact, but you can see what I am talking about. This color this region. Here it is indicated also the Bernoulli equation is not valid. Why? When the fluid is flowing, as it is moving from the left to the right, and it sticks to this solid body, then there is viscosity there, and therefore the streamlines, they indicate the behavior and they show that there is velocity. But away from this, away from the solid body, there is no viscosity, and therefore in that region the Bernoulli equation is valid. So that is away from this. But within this region, close to the solid body, where the fluid is sticking to the solid body, that is where it is not applicable. Similarly, acceleration of a particle, we come to that in a two-dimensional flow, the acceleration can be decomposed into two components. Streamwise acceleration, we have already shown these equations to you written down, so therefore I will quickly pass through it. And normal acceleration, that is in the direction of which is normal to the streamline, could be indicated as an equals to velocity square over r. So streamwise acceleration is due to change in speed along a streamline. Acceleration, the term itself, is the rate of change of speed. So change of speed has to be occurring whether it is positive or negative, and whether both possibilities are there, whether they are along the streamline or normal to the streamline, the acceleration can exist. And for particles that move along a straight line, an is equal to, this an is to be read as an in the subscript. And since the radius of the curvature is infinity, and thus there is no change in that direction. So in that direction, there will be no change as far as acceleration is concerned. The Bernoulli equation results from a force balance along a streamline. So therefore, the Bernoulli equation will normally exist along a straight line rather than in the normal direction. And if I try to show the equations, then you are familiar with these equations because I have already discussed them, and we have mentioned them when we were talking about the velocity field, the acceleration field, and so on. So they are the same equations, only trying to show how do we write when we are considering them along a surface, that therefore S is used for a surface, and if it is a straight line, a different term is used. For example, along x-axis it will be dx, it will be x. For y it will be y direction, that is for rectangular coordinates, and so on. So acceleration in steady flow is due to the change of velocity with position. And during the steady flow, a fluid may not accelerate in time at a fixed point, but it may accelerate in space. This we have already discussed as well.